Thank you. It's so great to come back and have gotten a chance to spend the day walking around the departments again, which look really different. You guys have grown a lot since I was here. So the title is a little bit intriguing, and I just finished getting tenure at Yale in the spring, in April, and so I just gave a talk there. And this to me was kind of the now what? And so I spent a lot of time thinking about that, and I've used part of that talk here for you today, because it's still relevant. So the big question, I think, is, and I'm going to call it doing the right things wrong, is, you know, we're really all focused on solving these sustainability challenges. It's become part of the ethos of engineering and design. And can we address these sustainability challenges if the designs we're putting forth are not in and of themselves sustainable? So I'll give you a couple of examples. The classic example comes from the Energy Security Act in 2007 when we set a renewable fuel standard. Locking in corn-based ethanol as the winner, the technology as the fuel of choice, and it turned out to be not a good pick, right? So this led to land use change and food price issues and water quality concerns from fertilizer applications, and potentially increased climate change impacts from converting marginal land to active in terms of growing more corn to meet this demand. So trying to do the right thing by addressing fossil fuel resources and climate change, but maybe doing it in the wrong way. Here's another example. So that's the Capitol building in Washington, D.C. back there. And this is a tanker car of chlorine that goes by still to this day 3 times a year carrying water to the Blue Plains water treatment plant in Washington, D.C. to provide clean drinking water. And so again, the goal here is providing clean, safe drinking water, meeting the Safe Drinking Water Act, but is moving these tanker cars of acutely lethal substances around really the best way to meet that goal. So doing the right thing, but again, maybe in the wrong way. The solar industry, so California just put out a report looking at how the future of economic development in that state may rely very heavily on this industry, but one of the constraints is the use of precious rare toxic metals in these photovoltaic systems. And so their question was, is there enough of these materials to go to scale? Is that going to be a constraint for us as we try to grow what is, right, addressing a necessary sustainability challenge in terms of climate change and air quality and providing energy? Crop efficiencies and those gains that were realized using pesticides, which we now know had human health and ecosystem implications beyond what they were intended to do in terms of controlling pests on these crops. Here's a study that came out of my lab as an example. These compact fluorescent light bulbs, which again was a regulatory requirement. So we picked a winning technology. We said incandescence should go away. We're going to use compact fluorescent light bulbs. Every compact fluorescent light bulb has a little bit of mercury contained in it. And when you do the analysis and you look at mercury emissions, so again, remember, we're going to compact fluorescent light bulbs to save energy in lighting technology in buildings. So now you've switched from burning coal or producing electricity for the grid to these compact fluorescent light bulbs. And it turns out a lot of the grids weren't releasing mercury because they weren't burning coal, or the coal they were burning wasn't dirty, didn't contain this mercury associated with it. So we solved one environmental problem of climate change and doing energy conservation by introducing more mercury into the environment in certain places in the country. So those states that are colored in orange actually have more mercury present in the environment than they would have if we had just stuck with incandescent light bulbs. So again, doing the right thing, but maybe not in the right way. So how do we get there, right? These are great challenges, great engineering. They're noble goals. We're addressing energy and water and climate and food, but the science is really exciting, but the question is, how do we wind up solving these sustainability challenges in these ways that aren't providing long-term sustainable solutions? So I'm going to argue we're playing this game of whack-a-mole. So this is this carnival game, right? And we have the climate mole pop up, and we take it and we whack it, and all of a sudden the water head pops up, and then we want to go after water and we use chlorine, and so the toxics head pops up, and on and on. And this is really how we tend to solve sustainability challenges, right? You hear often at industry meetings that people will say, I know climate's connected to water, and water's connected to food, and food's connected to pesticides, and so my sustainability goal is I'm going to reduce my carbon footprint by 20%. And they neglect all that nexus that they just talked about and set these single indicator goals and establish metrics for that and wind up creating more unintended consequences as a result. So here's the and therefore. So we need to do design differently. If we're really going to solve these sustainability challenges, we need to think differently about how we approach design, what the goals are, what the policies are. So EPA commissioned this report from the National Academies in 2013. And it came out and said, you know, the risk paradigm has worked for a long time. That's what we did environmental protection around. We want to reduce risk. But if you start looking at these new challenges like climate change, like emerging materials, like nanomaterials, like green chemistry, we need to move from a risk paradigm to a sustainability paradigm. We need to start looking at these nexi. We need to start taking into account multiple endpoints. We need to start having the conversation at a scientific and societal level about how we're going to weight climate versus water versus health, and how are we going to start designing these solutions going forward. And a lot of the argument is, well, you can't, right? So I've solved most of the problem, I haven't solved it all, and so this is the best solution I could put forward, corn-based ethanol. And you know, one response to that is, why'd you stop innovating? Why'd you stop designing? Why didn't you push further to try to address some of these other endpoints that are also of concern? So how are we going to do this? So this is what we do, right? As engineers, we do design. If you look at this curve, it's a pretty common engineering design curve. So from concept to detailed design to making something to end of life. And it turns out if you look at the design phase, you commit about 70% of the cost, even if you don't realize those costs, right? That's the break here until much later on. And so by making changes at the design phase, I can start to have effect on economics. And this is well understood. But the same is true for environmental impact. As soon as I pick a feedstock, I'm picking the process that's going to create that feedstock, and I'm also effectively designing my waste stream, what's going to happen at end of life. And so if I can intervene at the design phase, I can have this similar effect without having to realize those costs later on by thinking about it early on. And we really need to do this in an innovative way. So we need new ideas and new approaches. I would argue we're not going to get to sustainability with using the next least bad thing that's on the shelf. So we need to create those new chemicals, new products, new processes. How are we going to do that? So this is some of the work I did right at the very end of my time here, looking at what is a framework for doing design in a sustainability context. Principles of green engineering go across the life cycle. I'm not going to go through all of them, but you see things about using inherently safer materials, about trying to prevent waste, about using renewable feedstocks, about thinking about end of life ahead of time, about taking advantage of local material energy flows. What you don't see is the only principle being efficiency. And again, another argument I would make is we're not going to efficiency our way to sustainability, right? So we're not going to get there by just using a little bit less stuff. We need to think about the new chemicals, the new products that we need to get there. And I'm going to give you one example. So this idea of ideality, what does it look like when we start to approach this? So coffee right now is decaffeinated, largely globally today, still using methylene chloride. So most people don't go to Starbucks and order their double latte with a shot of vanilla and a little bit of carcinogen, right? But that's effectively what we're pushing up against. So one of the solutions to this was a new process that was coffee decaffeination using supercritical carbon dioxide. So supercritical CO2 is not regulated as a solvent by the FDA, so it's organic coffee. And I have now designed a green process to decaffeinate coffee. But what was the function? What was I trying to do? So I was trying to make coffee without caffeine. I wasn't trying to design a greener process to get that caffeine out of coffee. And so the ideal solution to this problem, to this engineering design challenge, might be to grow coffee beans, to grow coffee beans without caffeine, right? I don't need a chemical process. I don't need to use supercritical CO2. I don't need a greener system. I can just get that function I want in terms of coffee without the caffeine in it. So thinking about what is the function we want to provide and designing the sustainable solution for that function rather than incrementally improving today's process, today's chemistry to be a little bit greener. So how do you pick what problems to work on? There's a lot, right? And thinking about where to get engaged in sustainability is sometimes overwhelming. Sometimes you go to these meetings around sustainability and you walk out and it's kind of depressing because it's so overwhelming about what to get engaged on. And my argument is that we, one, need to get engaged, and two, you need to get engaged where you can have impact. So where are the highest places to have impact? And it's going to be at these nexuses, right? At the water energy nexus, the climate health nexus, because you're going to affect two systems that need to benefit, and you're going to more likely come out without unintended consequences by thinking across systems. I'm going to go through two case studies from my research in our group at Yale to try to highlight some of the work that we're doing given this framework. So the first one is around using bio feedstocks, renewable resources to make chemicals and fuels. So first of all, do you want to play in this space? Well, there's clearly an urgent need. I'm not going to spend time, but we know carbon dioxide and surface temperatures are going up. There's a policy driver here. The Energy Security Act of 2007 mandated a renewable fuel standard that we need to meet. The impacts from climate change are becoming ever more apparent. And there's a lot of questions around how green these biofuels are. So is this another example of the compact fluorescent light bulbs where we're putting more energy in than we're going to get out in terms of producing these biofuels? So the need is quite clear to get engaged in this space. One of the things that we approached this problem thinking about was we don't drill up a barrel of crude oil and say, I'm going to make gasoline out of this and the rest of it is waste. But if you look at how the bio energy industry has really started to grow up, I'm going to use the cellulose and I'm going to make ethanol, and the lignin, that's a waste product, and I'm going to burn it. For algae, I'm going to extract the oils that I can make biodiesel out of, and the rest of that is waste that I'm going to anaerobically digest and maybe recover a little bit more energy out of. So one of the first things we said is, what's all the work out there, just taking algae an example, of, if I took this algae and I pulled it apart into all its composite pieces, what can I do with the nonpolar lipids? What's the literature say? What about the polar fraction? What about the pigments? What about the starch? Polysaccharides, amino acids. So there's been a lot of work to say all of these parts of this biomass has value and has application. And so we wanted to keep this in mind and call it the integrated biorefinery. So I'm just like I have a petroleum refinery and I get out naphtha and kerosene and diesel and gasoline. I also want to approach a biorefinery in the same way. How do I know where to play, right? So I can't work on everything, and I have certain training to bring to bear to the problem. So we use a tool, life cycle analysis, to think about what the current hotspots on the system are. Why isn't it sustainable today? Why isn't algae biorefinery commercialized and running? So by doing life cycle analysis, so we took the base case of today's technologies that were on the market and being utilized, and then looked in the literature, we looked in the patent space, and we said, what are all the possible emerging technologies in the next 10 years that could be brought to bear on this problem, and how much better would the system look? So if you start substituting, right, instead of growing them in an open raceway pond, I use some kind of photobioreactor, there's some energy gain there. If I can use chitosan to flocculate instead of doing centrifugation, there's huge energy savings here. And in this part of extraction and conversion, there's a lot of energy associated with drying in the organic solvent system of getting the lipids out to do the esterification. And there was a group out in University of New Mexico who was using supercritical methanol. And when we did the LCA, that's the only one that came out. So I'm producing, this was done on a functional unit of 10,000 megajoules. And this was the only one still, right? 6,000 megajoules just for this life cycle stage. And so I still come out not energy positive, but I'm a lot closer. And so where do you want to get engaged in the system? So where are my opportunities? So there's lots of opportunities in the cultivation phase to try to get some energy gains out. We actually think there's a lot better we can do here than supercritical methanol, and that's the part I'm going to talk about. And then what you actually do with these credits instead of doing anaerobic digestion. So how do I get some other value, either economic or environmental, out of those other components of the algae? So just to give you a brief context, so supercritical fluids, I've mentioned them a little bit, but what it is if you take a fluid and you compress it, so up the pressure and then up the temperature, you reach this phase that's called supercritical. So it is a gas that now behaves like a liquid. So you get some solvency benefits out of it, and you can manipulate the density to change the solvency properties of the fluid. And then another little bit of context for those of you not working in the biodiesel or diesel space, the reaction that we're carrying out is a transesterification reaction. So you start with triglycerides. These are those lipids, the fatty part of the algae cell. You extract them using a methanol, and over a catalyst, you pull off one of those fatty acid chains and then add a methyl ester onto it. So you get fatty acid methyl esters FAME, which is your biodiesel. You're left with a diglyceride. You undergo that reaction again, monoglyceride to glycerol. So this results, and you get 3 moles of FAME for every mole of triglyceride that you start with in the system. Okay, so to start with, these two things are insoluble, triglyceride and methanol. So there's a lot of energy associated with heating up that reactor to get that reaction to go forward, and there's a lot of work around trying to get catalysts that'll carry out that reaction. So our idea was, could we use CO2 not only to do the extraction of getting the solvency of getting these lipids out of the algae, but can I actually use this to carry out the reaction in the same reactor? So can CO2 behave like a solvent and get that triglyceride and methanol to interact? So the first question, any green product, green process, green chemical, that you need to ask is it efficacious? Does it work as well as what's on the market today? What's the alternative that you're trying to replace? So these graphs are a little bit busy, but at 100% converted to FAME, this is the equivalent of what I would get if I was using an organic solvent. So these are normalized to using a chloroform methanol extraction and then conventional conversion to fatty acid methyl esters. So at 100%, you could see there's some conditions of pressure and temperature where I'm reaching or exceeding that 100% mark, and I can manipulate temperature and pressure to get there. So yes, our system works. That just tells me quantity, that I can get as much biodiesel produced as a conventional system. The next question you need to ask is quality. So those lipids, those triglycerides, come in many different chain lengths and different degrees of unsaturation. So the next question was to look at what are we making. So Bly and Dyer, this is that conventional organic solvent system. And you can see that what we're getting in our supercritical CO2 system looks on par, equivalent with what is coming out with Bly and Dyer. But there are some differences here. So the first thing we said was, this is great because we can make biodiesel. We can do it in CO2. We don't need an organic solvent. But this also started to give us some hints about pulling that algae apart into its requisite components. Now, are we better than the conventional system? So the one thing that we, of course, wanted to look at was water. One of the big energy consuming aspects of making algae biodiesel, or any biodiesel, is drying the biomass before interacting it with the organic solvent. So we dried ours and then started adding in requisite amounts of water, and you can see that very little impact on how much FAME we were producing out of the system. So we don't need to dry our biomass. So there's a huge energy savings there if you think back to the life cycle analysis. The other thing is, when you extract with an organic solvent, you get this kind of black, really dark green looking stuff. So I'm pulling out a bunch of stuff that's not triglycerides, right? So there's those pigments that are in there, there's carotenoids, there's xanthins, there's a bunch of other molecules that come out when I do a lipid extraction. And by tuning my CO2 system temperature and pressure, I can actually selectively start to pull out those lipids and actually control how much of those other components are coming out. So again, I'm starting to get some knowledge about how to pull that algae apart so that I can recover high value pure components rather than turning everything into biodiesel. So this is some unpublished work, but where we are now is starting to look at changing carbon dioxide flow, temperature and pressure over the system, and looking at, I can start to pull apart these chains. And so I can start to enrich these fractions for omega-3, omega-6 fatty acids, which have a much higher economic value than biodiesel. I can also start to separate out those which are relevant for biodiesel production versus those that are relevant for jet fuel. So I'm starting to get increased value out of this same biomass by being able to pull apart fractions that have higher economic value in different end-use applications, which almost makes your biodiesel become a waste of this other process of trying to selectively extract different components. Okay, so we can extract, we can do it with wet biomass, we can meet the same efficiency, and we can be more selective about what we're pulling out. But can we do the transesterification reaction in the same reactor? So this is a big thing, because normally you do your lipid extraction, you're extracting into an organic solvent, and then you need to find your biodiesel, FAME, which is also soluble in that organic solvent after the reaction. If I can do that inside my supercritical reactor, when I flow out and I release pressure and I cool the temperature down, I will recover a CO2 stream and I will be left with biodiesel without having to do any distillation work at the end of the reaction. So my PhD student, thankfully, was very grateful that there was one condition of temperature and pressure and methanol loading where we could carry out a transesterification reaction above 90%. So I've extracted that lipid in this reactor and then added methanol and a catalyst, and I'm able to produce FAME, biodiesel, on par with what I get from an organic solvent extraction. So again, in a one-part reactor. We lose some of the efficiency, so there's some loss here, 7 to 10% versus the organic system, but we're not drying our system and we don't have to do distillation at the end. So there's some trade-off there, but ultimately, if you do the economics and life cycle analysis, that little bit isn't worth going after because of all the other gains. And I think this system can be further optimized. Okay, so we can't optimize it unless we understand what's going on and why it's working. So one of the other important things to think about with supercritical systems is how many phases do I actually have present inside that reactor? So I told you I have CO2 in there. I told you I have methanol in there. And I also have the lipid, that triglyceride that I've extracted. So you can see some of the lipid here, and then you see this kind of cloudy system. And so I actually have 3 phases present here. So I have that lipid triglyceride phase. I have a methanol-rich phase that has some CO2 in it, and I have a CO2 phase that has some methanol partitioned into it. And as I change temperature and pressure on the system, I can actually make one phase. So I can solubilize all of those into one phase, and that's in a supercritical phase. When we went back and started looking at what is the system condition that actually delivers this really high yield for biodiesel, I'm actually better off being in a 2-phase system. So the hypothesis here is that being in one phase is providing a feedback. So I'm actually building up biodiesel in the system, and so the reaction is being inhibited. If I'm carrying out this reaction in 2 phases, the FAME is partitioning up into the CO2 phase and is actually leaving the reaction site. And so I'm better off having this methanol triglyceride phase. Those are the 2 things I need to come in contact in the presence of a catalyst, and having a CO2 phase available for the product to partition into. Okay, and then the other thing is, what is that 7 to 10% that's not going? Where's the reaction getting caught? Is it getting caught at diglyceride? Is it getting caught as monoglyceride? How do I overcome that barrier? So we're starting to look at those questions again. This is just some preliminary results, but you know, is it getting stuck as 1,2 diglyceride, 1,3? And then it's not the monoglyceride we're worried about. So now we need to go back and optimize the system to think about what these reaction products are and tweak the solubility of that system so that the diglyceride is now present in that bottom phase. Okay, And then the other thing is, this is great, it works for algae, but it turns out DOE really hates algae. It was not a popular substrate to be doing research on for renewable energy for a couple years. So we started looking at canola and palm oil. It doesn't matter to our system what we put in there to extract and to transesterify. And so I've just put up here again those triglycerides, so C16 with no degrees of unsaturation, and then however many degrees that's there. And these are all present in the algae. So it's things we've seen before at different combinations and different ratios. So what's green converted to FAME, and what's yellow was unreacted either as triglyceride or it's stuck as some kind of diglyceride for canola and palm oil. What we were using when we were doing this was catalyst beads. We were using a naphion, and it was in its bead form. And so one of the ideas was, we're getting not great conversion on this system because the surface area and the contact and the internal diffusion to the bead, which swells inside this system, was not ideal. And when we switched to a catalyst powder, so again a naphion, but using it at a much smaller particle size, you get much better conversion. So this brings up questions of mixing and how to, again, optimize the system, which we're continuing to work on now. Then the question is, when you have these big mixtures, what's getting converted? So when you start looking, the FAME yield, the system's much better for shorter chain than it is for longer chain. And the more I up the temperature, the more conversion I see. And if you do the statistical analysis, it turns out that log P is the most significant predictor of which part of that triglyceride portfolio is going to get converted to biodiesel. And it has to do with where it's partitioning in that multi-phase system inside the reactor. So again, we have some more information about how to further optimize the system and improve it. So what does it look like? Where are we headed with this? So here's our idea of what an integrated biorefinery might look like. Here's our extractor. We have biomass in it. I'm going to extract those triglycerides and flow them into a parallel reactor where the reaction is happening for making biodiesel, pulling out PUFAs. I can recycle and use methanol in the system to make that biodiesel. And then from the extractor, after I pull out these lipids, I can now tune temperature and pressure, add co-solvents to go after these other value-added components. So we're now pulling out carotenoids, pigments, and xanthins after we've done our lipid extraction. So I'm not losing any value by going after biodiesel, and in fact, it's giving me a cleaner matrix to go after some of these higher value components. And what you're left with at the end is starch and protein, which turns out to be really good for animal feed. Or you can ferment this starch side to make ethanol or some other end-use applications. So that's where we're heading with this system. But again, starting to think about the nexus of this system in terms of how do I get the most economic and environmental benefit out of that biomass that I'm starting with. Okay, so I have a second case study, again, kind of highlighting this approach, and it's around green chemistry and looking from a molecular basis as well as from nanomaterials. So again, I'm going to argue there's an urgent need here. So these are some of the headlines that I've pulled over the past couple years that the public are seeing. Okay, so Walmart is recalling lead-laced baby bibs. Nanotechnology is a danger according to Business Week. Science came out with a report about formaldehyde in your clothing. The Canadians have banned bisphenol A from these thermal receipts because it turned out you were being exposed to endocrine disruptors every time you signed your credit card. Bloomberg News said nanotechnology risks are going the same way as GMOs. We should just abandon it like they did in Europe. Fast Company came out, nanoparticles might be the future, but they might also be really bad for you. And even your shower curtain is something you should be concerned about. And it just goes on and on and on and on and on, right? So these headlines aren't hard to find. And if you're the public and you're not trained in this space, what is your reaction to this? Be afraid. Be very, very afraid, right? So some chemicals are bad, and we don't know which ones, and so all this stuff's in your products, and so you're going to get cancer, you're going to get exposed to endocrine disruptors. It's scary stuff, right? And One of the things is some of these chemicals have a function that's necessary, we need. They're in the commodity space or specialty chemical space, but does the function necessitate the hazard, right? So are the same properties that are controlling the function of these molecules also dictating the hazard that's associated with it? And if we can separate those two things and I can start control properties so that I get function without hazard, that would be a pretty cool trick. This is the end result of this. I actually saw this on the shelf. Burt's Bees selling chemical-free sunscreen with hemp seed oil. Right, so if hemp seed oil is not a chemical, what is it? But this is what the marketing has gotten us to, right? So some mom is, and I'm a mom, so I'm not picking on moms, but some mom is going to the store and saying, this is safe, I'm gonna buy this for my kid because it's chemical-free. So we have a big job to do to the public about not all chemicals are bad, and we actually can nuance the dialogue about safe versus unsafe, or safe versus those we're concerned about. The challenge with this is, and this is a quote from Linda Bierbaum, who's the head of NIEHS. We kind of jump from the proverbial fry pan into the fire when replacing chemicals. So her argument is that we go from something like bisphenol A, which we're concerned about, and again, if you go to the store and you look now, lots of like Nalgene water bottles will say on them bisphenol A free. So people buy them, and that's great, but they don't ask the next question yet of what'd you put in there that was providing the function of bisphenol A as a substitute, and is it any better than bisphenol A? And it turned out that the industry moved from bisphenol A to bisphenol S, which also has endocrine disrupting concerns. So how do we know when we make a substitution that we're making a good choice in terms of, again, maintaining that function without subsequent hazard? And the problem with this is there are really two big things. One, there are too many chemicals. So there's 90,000 chemicals in commerce, in the market, that has gone through EPA's pre-manufacturer notice. EPA historically has been very slow at looking at these chemicals, and the regulatory environment under TSCA, the Toxic Substances Control Act, says you don't need to provide any toxicity data to us unless you have it. So how many companies are going to collect that data, right? So the burden is on EPA to make a judgment whether this should go forward and be allowed to be produced or not. And in the absence of data, they're doing modeling. And it's slow, and they need training sets, and it takes a long time to generate that data. One of the ways that data is generated, of course, is animal testing. So again, an incredibly high cost in terms of resources and animal life. And we still don't have enough data to avoid all the headlines that I just showed you a minute ago. So the system isn't quite working the way it's supposed to. I'm not going to spend a lot of time on the molecular design side, except to say we've been able, for aquatic toxicity endpoints, these are 3 different aquatic species. I'm plotting here log POW, right, which is the octanol water partition coefficient, and delta E, which is the difference between HOMO and LUMO, so it's just a measure of reactivity. All these green dots are ones that EPA has said are safe from an aquatic toxicity standpoint. I'm not concerned. And all the red ones are ones that are medium or high risk for aquatic toxicity concern. And when you start plotting them, I mean, there's a lot of work to figure out all of these individual molecules and then, predicting physical chemical properties for all of them, and then looking for the correlations for the relationships. When you start to do that kind of analysis, you can see that this upper left-hand quadrant, most of the green clusters there. So if I'm going to design something new and I'm worried about aquatic tox as an endpoint, I'm more likely to have something safe if I design within these guidelines. And maybe more importantly is in this bottom right quadrant, I don't see any green dots. So I'm much more likely to design something that's of concern if I'm in this space. And then there's a lot of work to go in and pull out what these dots are that wind up on the other side. So this one turns out to be a phthalate. So EPA said it's not of concern, but there's a lot of literature to say this probably should be red. And then what are these red dots that are over here? And some of them are ionizables. So when we're modeling physical chemical properties, we need a pH. And we might be predicting the wrong form depending on what pH we're at. So there's a lot of work to do to refine this, but you can start to get some information on that 80-20 rule of, am I more likely or less likely to design something that's safe or unsafe? Okay, and then can we use this for nanomaterials too? So can I take this same idea about molecular design and apply it to the field of nano? So one of our first questions was, for single-wall carbon nanotubes, if you go into the literature, the toxicity information is quite all over the map about whether they're toxic or not. A lot of it has to do with different batches, different manufacturers, different functionalizations. So what we did is we bought one set of carbon nanotubes, we purified them, and then we functionalized them using all of these different functional groups. So we derivatized them. So we had the same starting set, and the only difference within the set was what we added to the surface of the nanotube. It turns out that for single-wall carbon nanotubes, the story is really an aggregation story. So it didn't matter so much about the properties or what I was putting on the surface, but it mattered about the fractal dimension. Was it more rod-like or was it more sphere-like? And it mattered about whether they were aggregating into many different sizes or into one size. And so you can start to see that there's this delineation between those that are not toxic versus those that are. So it becomes a story about aggregation. And so this is great because if you're somebody who's trying to use single-walled nanotubes in an application and you're worried about unintended consequences or toxicity, here's a parameter you can measure. How valuable is this is we took one of these that was non-toxic, safer than the rest, this functionalization, and then we put it in a wiggle bug. So we cut it up to smaller pieces and converted it, its aggregation state, to this open square here. So by changing the aggregation of this material, I was able to take something that was not toxic and demonstrate that by changing aggregation state, it fell in line with what we predicted would be a toxic material. Okay, that's great for single-wall nanotubes. It turns out these aren't really that popular. They're really hard to work with. They're hard to disperse. Much more application going on in multi-wall nanotube space. So we started in the same place. Is this really a functionalization story? So for multi-wall, where we started was we're just going to put a bunch of oxygen on the surface. So you treat them with nitric acid or some mix of nitric and sulfuric acid, and I put a bunch of oxygen groups on the surface. And you get a mix of the kind of oxygen groups that are on the surface. It turns out if you start annealing these, you can do selective reduction. So these groups are labile at different temperatures, and things like carboxylic acid will come off first, and things like carbonyl groups will hang on for a long time at higher temperatures. So this is a handle to start manipulating what's on the surface to see if we can see a relationship to toxicity. So I'm not going to go through a ton of this data except to tell you that as we annealed up to those carbonyl-like groups, you see an increase in toxicity. And as we continue to heat them, those carbonyl groups eventually come off. And then there's a lot of literature to say that you start healing tube defects. And so you get a much purer 6-member ring, complete multi-wall carbon nanotube, and the toxicity goes down. And this is just data from 2 different manufacturers to show that this wasn't unique to the batch that we were working with. Okay, the other thing we did is we just took that same starting material and we used increasing amounts of nitric acid, when the idea here is to just get more and more oxygen on the surface but not manipulate what form it's in. And it turned out that just putting more and more oxygen on the surface actually had very little impact on toxicity. So this is something unlike the single-wall nanotube story. It's something about the kind of surface functionalizations that are on the tube. So we worked with a group at Johns Hopkins who does chemical derivatized XPS. So they can actually start to delineate carboxylic groups, right? From these purple ones, from hydroxyl groups, from carbonyl groups. And then there's some stuff that we couldn't classify, and those are in blue. So here's my acid-treated sample that I started with. When I annealed it at 400 degrees, you can actually start to see those groups come off, the carboxylic acid groups come off, and you start to see the carbonyl groups have a higher percentage of what is left in those, what form the oxygen is that's on the surface. Same is true, so this is just again from that other manufacturer. and you start to see carboxylic acid groups come off, and the carbonyl groups have a higher percentage of what the oxygen groups are on the surface. When we did it for those that were just adding more and more oxygen to the surface, we used a higher percentage of nitric acid. You just see more oxygen come up on the surface, but it's kind of the percentages stay of what is being added to the surface of the sample. So carbonyl groups are known to be reactive. They're known to have enhanced reactivity. And so we went and did oxygen reduction reaction measurements. And you see that, just like you would predict from having carbonyl groups on the surface, that you get this shift in the curve, and that's actually enhanced activity towards oxygen reduction. So these have a higher electrochemical activity. They're more reactive. And surprisingly not, the more reactive they are, the more toxic they are. But we now have a mechanism, and we understand how to manipulate that in terms of what the application is for these multi-wall tubes. So we use glutathione as a biomarker, but you can carry this out with other reactions, and we're generating ROS at the surface of the nanotube. So that's how you're getting your electrochemical activity, but that's also causing cell damage and causing toxicity. So there's a lot of work to be done. Are these singlet oxygen? Is it ozone? How is this chemical reaction actually happening? And that's some of the mechanistic work that we still need to do. So right now we still have a correlation, but we don't have a very clear mechanism except to say it's something about the reactivity. One way to think about this, and some of the future work we're doing is, does this work for nitrate and amine systems and sulfate and thiol systems? So is it about the reduced form that's on the surface? And can we, again, relate those properties back to the functionality that we're interested in, and then what the hazard and exposure are? So can I pull apart property from function and hazard? Okay, so those are my two case studies from my lab. And I'm just going to spend a few minutes talking about what I think some of the big future challenges are going to be in terms of sustainability and environmental and chemical engineering as we go forward. So one of the first ones is this whole idea of making. So it's not just the guys from Breaking Bad, right, who are in their basements, but there are lots of people like that who are making lots of stuff, and it's become decentralized and democratized to the point that this guy, Taylor Wilson, built a fusion reactor in his garage at the age of 15. So what is this going to mean? Instead of being EPA and be able to regulate what chemicals are in commerce and what are being released to the environment, what happens when people start doing this in their basements and garages in these maker spaces? Then there's some really interesting stuff. So you can do printing, and 3D printing is known, but there's work now on 4D printing. So if I make materials that are sensitive to environmental conditions, not only am I going to be 3D printing these materials, but when I set them in place, they're going to change form. So again, thinking about what are some of the environmental implications, what does this mean for all of the products that are on the shelf when we start thinking about life cycle assessment, or what the environmental impacts of manufacturing are, or the carbon emissions associated with a supply chain, if this all becomes what people are doing as individual consumers. Okay, I think another big challenge, and I heard a lot about it as I was visiting with different folks today, is this idea that the world's getting hotter and flatter and more crowded. So what is the role going to be in terms of this next billion, 2 billion, 3 billion people, where they're being added, right, which is in developing communities? What technology have we developed that makes sense, and what new technologies do we need to develop that are more appropriate for that context? So thinking about taking our engineering ideas, our concepts, our knowledge, the chemistry, the biology we know, but now designing systems that are appropriate for the context that we're working in, and thinking about what that looks like for these developing communities. This is a really, I think, important issue. So Rosie the Riveter said we can do it, and if you look at where that's going now, it's towards these science, technology, engineering, STEM disciplines. So this is a cartoon. I love this. This year we made great strides by doubling the number of women in engineering, because now there's 2 girls in our class. Right? And if you look at the statistics, it's not that funny, right? So engineering is this pink line at the bottom, and this is the number of BAs in the field received by women. So we're still hovering below 20%. And I just told you there's all these huge challenges. And if we're missing half the population from the dialogue, how are we going to come up with the solutions that we need to come up with? So, right, engineers is what we do. We solve for X. And so I have a sabbatical coming up, and my project is going to be solve for XX. So what does this look like when we start to think about what we need to do, how we need to teach, how we need to train differently to engage more than that hovering around 20% of women in the field? Then my next question is, what are we training our students to do? So how much of our education work is theoretical, right? Assume a spherical cow in a vacuum, and then you can solve your problem. This is like serious about how we're going to manage to train our students as the problems are getting more complex, more nuanced, more diverse, more democratized. And so, you know, it really looks something more like this. It's pretty messy. And I stole this slide from Rick Oakes. You know, if you start looking at the corn-based ethanol system and who really needed to be involved in the discussion before the renewable fuel standard came out, it was all of these disciplines. And so thinking about how we're going to start training our students at these interfaces to do this work at the nexus. And what does interdisciplinary really mean? Is it just two people from different fields coming together? What is the breadth versus depth discussion that needs to happen of having been trained in a specific discipline versus being able to be broad enough to engage across some of these broader questions? Okay. And then this idea of systems is not one that we're well versed in terms of the education and training that we give. So this idea that the main fallacy in this kind of thinking, reductionist thinking, is that hypothesis does not mean that it's a constructionist one. The ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe, right? So historically, we've rewarded people because you hold every other system condition constant, you change one parameter, and you report how the system behaved differently. But when you start moving all those parameters at the same time, there are feedbacks in the system that we don't capture doing reductionism. So how do we need to think about changing what's rewarded, what scientific publications look like in terms of reductionist thinking versus getting towards this meta systems approach? And it needs to happen. I mean, I kind of started at the beginning that, you know, we know there are all these nexuses exist, and it gets more and more complicated as you add more layers and more systems into the picture. So I've done some work starting to think at the water energy nexus. We put out a paper that showed if San Diego, California had done water conservation, they could have met their carbon goals at 50% of the cost than trying to green up the electricity grid. And it would have been great because they have this huge drought problem right now, and they would have solved a water problem and their carbon problem at the same time. Okay, so, right, this is often where we focus our research, what's the cause versus the effect. There's lots of stuff going on in the system we need to think about. I always tell my students, I feel like this, right? Maybe pushing on that wall to the right will give me some space, and this is what winds up happening. Right, and we don't want to get crushed, so we need to start thinking differently about what's going on around us. So we need that five-headed hammer, right? This whack-a-mole game is real and it's happening. And we don't want the mole to turn into this, and that's what it's starting to look like for some of these systems that we're worried about, like climate, right? What is the tipping point? And if we're really good at this nexus technology, this is what happens, right? The moles start beating each other up, and we don't need to play the game anymore because we're solving water energy nexus, food, waste nexus ideas at the same time. So lots of sponsors to thank. I went through a lot of research that we've done in my group over many years. We've been really lucky to have a lot of support from a bunch of different folks on what we're trying to do. My group, who has a really big fondness for making pyramids, I will call out Lindsay So, who did a lot of that work on the biodiesel system I showed, and Leanne Pasquini, who did a lot of work on that carbon nanotube system. I'm also very fortunate to be part of a bigger center at Yale, which is the Center for Green Chemistry and Green Engineering. So it's my group and several other groups that come together across chemistry, engineering, and the School of Forestry and Environmental Studies to work on these sustainability challenges. And I have lots of collaborators across engineering, School of Forestry, and the School of Management. and at other universities and internationally. So I just want to acknowledge all of the help we had in the work I presented, and I'm happy to answer any questions you might have. Thank you.
Our bodies don't absorb everything, and so the rest gets flushed down the toilet. Some of it ends up in our lakes and rivers, and can cycle back to our faucets. What do we know about drugs in the water?